Welcome back to our course on trusses. Let us have a truss that combines many ideas of previous lectures, and let us pass through it to master truss analysis. We have our truss here, our first truss, 20 tons external load on D, 20 tons on joint O6, 10 tons on joint O4, and the truss is symmetric. And since the truss is symmetric, YA equals YB equals half the 80 tons each carries a vertical reaction of 40 tons. Now we need to calculate XA, the horizontal reactions at A and B. This couldn't be done unless we have moments about C. But to have moments about C, we need to have a cut passing through members 1, 9, 14. We will face another problem that we don't have member 1, the value of member 1. And therefore, the clue is to start with members 1 and 2. Or in other words, open the truss here and remove joint D. This is done by equilibrium of joint D. Just before starting this equilibrium, we recall that this is the compression internal force in a member. The arrows are heading towards the joints. Here we have our joint D with the external load, 20 tons. To maintain equilibrium in the y direction, we need forces of total 20 tons heading upwards. They can be achieved by analyzing members 1 and 2. The vertical component of each member equals half these 20 tons because of symmetry. Here we have, those are the components, vertical components of members 1 and 2. And thus, F1 is heading towards the joint D, and therefore we can conclude that it is a compression force. Similarly, F2 is a compression force. We need a relationship between F1 and F2. From symmetry, we can conclude that they are equal, or in other words, we can have an equilibrium equation in the direction of X at D. Going back to our truss here and considering joint D, those are the arrows heading towards joint D internal forces. So those are the horizontal components and the analysis. We know that theta here is 45 degrees. Sigma forces in the x direction equals 0. We conclude that F1 equals F2, or just from symmetry. Predicted compression, as we previously explained. Equilibrium in the y direction equals 0. Then both components and the 20 tons must be 0, which gives F equals 14.14. F1 equals F2. Just compensate or substitute for each by the symbol F, and we get 14.14 tons compression force as predicted before. Going back to our truss, we analyze joint D. Now we will just remove it and have the internal forces of member 1 considered at O7, the internal force of member 2 considered at the other joint. And therefore, and therefore we just remove forces at joint D and apply the forces of members 1 and 2 at the other joints. Now we can consider that we have an open truss here, and therefore we can easily deal with joint C. So, considering moments at joint C, for just one part, say the left part, we can compute XA. We have 10 tons at O4 and the arm 3 meters until we reach C. We have 20 tons at joint O6 and an arm 9 meters until we reach C. We have the force F, the force in member 1, multiplied by the arm perpendicular to the link member 1, which is 3 divided by sine 45, or in other words, the distance CO7. And at last, we have the 40 tons, reaction YA multiplied by the arm 6, and the unknown we are searching for, XA, multiplied by this vertical arm 3 meters. This gives that XA equals minus 10 tons, indicating that we assumed its direction incorrectly. And the correct direction is opposite to what was assumed. Similarly, for XA at the other support. Now we move to members 9 and 10 to compute them. From symmetry, we can conclude that F9 equals F10. But we can also conclude that each of them equals 0 just by inspection. Let's try this inspection before calculations. Now, from symmetry, member 9 and member 10 must have the same force and therefore must have the same vertical components. Considering tension force, then the vertical component of 9 heads upwards and the vertical component 10 heads upwards. But then, both forces heading upwards, equilibrium is not fulfilled at C. Sigma forces in the y direction at C doesn't equal 0, and therefore the only way to fulfill both symmetry and equilibrium in the y direction at C is to have the force in 9 equals 0 and the force in member 10 equals 0. Of course, we can reach the same conclusion by computations. Consider section S1 and just take the equilibrium in the y direction for part of the truss, let us say the left part. Forces in the y direction are the green 40 tons YA, the blue 20 tons at O6, the blue 10 tons at O4, and the vertical component of force F1 heading downwards. And if you consider tension force in member 9, then the vertical component of member 9 will be heading downwards also. In this equation, all forces heading downwards have a negative sign, and those heading upwards, which we really have one force heading upwards, YA, has a positive sign. Substituting for F1 by this value, we conclude that F9 equals 0 tons. To proceed with our truss and compute members 3, 4, and 5, let us start with member 3 and revise our K-truss. We have this snaky section S2, S2, passing by 4 members, member 3, member O3, O2, O2, O1, and this horizontal member at the bottom chord. Considering sigma moments about O1, we'll just cancel 3 of the 4 cut members. Those are the horizontal member O6, O1 and the 2 vertical members here, and we are left with one unknown member 3, which of course you need to put the arrows assuming tension force, extract the section outside if you need, but we are just having a quick revision. Joint O2, here is joint O2. Inclined members are F4 and F5, and we are not really concerned with the vertical members. So those are the components of F4, those are the components of F5, and we will consider equilibrium in the X direction, which gives that F4 equals minus F5. Remember, while studying the K-truss, we concluded that the easiest way, or one of the easiest ways to calculate the internal force in the two members forming the K shape, like members 4 and 5 here, is to take two equations in two perpendicular directions. Maybe one from a joint method and the other from a section method. So this is S3, S3. And here is our section considering equilibrium in the Y direction. We conclude that F5 equals 22.36 tons, and therefore F4 is a compression with the same value. Here we are. We had joint 2, equilibrium in the horizontal direction, and section S3, S3, equilibrium in the Y direction. Easiest way to compute F4 and F5 forming the K shape, considering joint O3 to get member 6 from the equilibrium in the horizontal direction or in the X direction. This directly gives that F6 must be equal to F3. And joint A, taking joint A, we can compute members 7 and 8. We need an equation that contains one unknown. If you consider the Y direction, we will have two unknowns at A. One of them is the force in member 8, and the other the component of the force in member 7. Therefore, it is really wise to start by the horizontal direction. Sigma f of x equals 0 gives that xa must be in equilibrium with the horizontal component of F7, and therefore F7 has the value 14.14 tons tension. Now we can apply the equilibrium in the Y direction, because after substituting for the value of F7, it is known now, we can conclude F8 to be minus 50 tons. Compression. To continue with our truss, let us consider section S4, S4. Now we need to compute forces in member 11 and 12. Section S4, S4, and considering this section in the closed pink square, we don't really need to extract it outside now. After computing many trusses and with some concentration, We can write down the equations directly without extracting the section outside. It only needs training. So considering the forces in the y direction, we have external forces 20 tons at O6, 40 tons at A, and considering the internal forces, we consider the members that had the cut passing through. Now, S4 passed through 4 members, 6, 11, 12, and 7. 2 of them are horizontal, 6 and 12, and therefore they are not included in the equilibrium of the y direction. So we are left with members 11 and member 7 because both of them have components in the y direction. And here is our equation. Member F7 was previously computed from the equilibrium of joint A, and we compute F11. Considering forces in the x direction, we already computed the force in member 6, and we are left with member 12 unknown. Of course, all other members are previously computed. Just substitute for their values and we have F12. We consider joint O4, extracting it outside. Of course, by training you may not even need to extract it outside, but let's do it for now. We have 4 members connected to it. Member 7, member 12, 13, and 14. We have one external force, 10 tons at joint O4. Now, let's consider which members are previously computed. For the equilibrium in the y direction, we have forces in member 13 and 7. 7 is previously computed, so we have one unknown in one equation and we compute F13. For the x direction, we have members 12, 14 and the component of member 7. We already computed F7, F12, and we are searching for F14. Considering joint O5, we have members 3 and 4 and 16 connected to the joint O5. We really don't need to extract it outside. We know that members 3 and 4 are previously computed and we are left with one unknown, F16. Member 16 is vertical and therefore we should consider forces in the vertical direction to get this one unknown. This gives F16 equals 10 tons. This is really the sequential technique of thinking. We just consider which member we need to compute, in which direction, and we consider equilibrium in this direction. Considering now joint O6, we have 3 members still connected to it. Member 16, we've just computed it. Member 5 computed from the K shape, and we are left with the one unknown member 15. Member 15 is horizontal, therefore we should consider equilibrium in the horizontal direction. This gives the value of the force in member 15. Now taking joint 7, we inspect the forces connected to it. All those forces are previously computed. So we can have this joint or any other joint or any section you are convenient with just to check our computations. This is good practice. You can consider forces in the x direction or the y direction or both. Let us have one check forces in the y direction. We have F13, component of F11, component of F9, and component of F1. We substitute for the value of each force in this equation and we just make sure that it is fulfilled. In other words, it equals to 0. So, after computations, yes, the equation is correct and equals to 0, which means that we computed those particular forces in those particular members correctly. This concludes some collective ideas with our first truss.